Hi, everyone. I'm Michael Shapira from Compare Labs. I'm giving both this talk and the next, so apologies in advance. But also, I actually view this as two parts of the same talk. What I want to do in the first part is give you a taste of the algorithmic foundations of what we're doing through a very simple toy example. And then I want to talk about some results we get in the field, and this is joint work with Telefonica. So no need to elaborate on this in this forum, right? But the way we deliver content hugely impacts quality of experience, be it in terms of the video bitrate, the time spent rebuffering, the lag behind live. And when we're talking about content delivery, we're primarily talking about congestion control. We have different traffic sources sharing the same network resources. We have to pace their rates if we want them to make good use of the network. But there's competition between these users, and the network segments themselves might be challenging, right? Think LTE or 5G, volatile networks, and so on. And the issue is, if at some point in time we send too slowly, we won't be able to support the video in HD. If we send too quickly, we might overwhelm the network, leading to data being lost, data being delayed, and consequently, bad quality of experience, like video rebuffering. And the starting point for this work, a while back, was the realization that the core issue here is that content delivery is one size fits all, right? The internet doesn't care about whether you're sending video traffic or other kinds of traffic. It doesn't care about whether you're sending live streaming or VOD. We're using the same one-size-fits-all mechanisms to deliver these traffic, even though these are very different animals in terms of what they want from the network: throughput, latency, jitter, and so on. And in addition, we're using the same rigid logic regardless of the network. We're operating in the same way regardless of whether we're sending over 5G towards a mobile device or over a wired connection towards a smart TV. And not surprisingly, when you expect the same algorithmic approach to perform well across a daunting breadth of application domains and across a daunting breadth of network conditions, it typically fails. Right? And indeed, all of these one-size-fits-all congestion control algorithms have their own kryptonite. Right? So what we're trying to do is to automatically tailor the content delivery logic, the congestion control logic, to what the service actually requires from the network and to the prevailing network conditions with respect to the specific users we're sending traffic to. So as I said, I want to illustrate the essence of some of the algorithmic ideas here through a very simple scenario. You have a single sender sending traffic across a single link. Right? So you're repeatedly sending video traffic across a single link. And the link has certain characteristics. There's the bandwidth of the link. There's the latency along the link, the physical latency. There's the size of the buffer in which packets are stored. There's the amount of non-congestion-induced loss. Right? Think of physical layer corruption, user mobility, and volatile bandwidth, and so on. And what we want is to be able to, over time, change the logic of the congestion control algorithm so as to make the best use of the link with respect to what the service actually cares about, the quality of experience metrics of the video. So from a theoretical perspective, this is actually a multi-armed bandits problem. Multi-armed bandits is a sub-area of machine learning theory, where you have a decision maker that has to repeatedly select between actions in the face of extreme uncertainty. And formally phrased, we have a decision maker. At each point in time t, the decision maker chooses an action, AT, and only after the fact does it learn the empirical consequences of choosing that action. So this is termed the reward, RT. So think of the action as inducing a reward in some probabilistic way. Right? We're not dealing with a deterministic environment. So there's certainly stochastic effects affecting the link delay, the packet loss rates, the congestion control algorithm itself, packet level phenomena, and so on. So what we want is to choose the action that in expectation is the best. And this immediately translates to our environment. The sender is the decision maker. The strategies or the actions are different configurations of a congestion control logic or different congestion control algorithms you could choose from. And the reward is the performance score. I'll get back to that, but think of something that takes into account, for example, the video bitrate, the rebuffering times, and so on. Or if we're talking about transport layer statistics, how much traffic I got across, what was the packet loss rate, and so on. So had we known the model, had we known exactly how each configuration affected performance, we would have simply chosen the best one. Why is multi-armed bandit theory interesting? It's interesting because there's an inherent tension between exploration and exploitation. Right? I want to choose good actions. But to choose good actions, I have to try out different actions. I don't want to linger too long on trying out different actions, because in doing so, I'm actually suffering bad performance because of choosing bad actions to experiment with. So you want to balance these two things, probing different configurations for sufficiently long to learn valuable information about which one is best, but then sticking with the best one. And there's different algorithmic approaches in the literature for doing this. Epsilon greedy, upper confidence bound, softmax, and many others. And I want to show you this in action in a very simple controlled experiment. Again, single link, single sender, 4-candidate congestion control configuration. So what we're using as the congestion control logic is PCC, which is an online learning-based congestion controller that can be configured in different ways. It has configurable parameters. I'll talk a bit about this in the next slide. And what we want is to be able to choose the best one over time by repeatedly interacting with the link. What we vary in our experiments are the link parameters and the configurations. So links in our experiments are going to have different bandwidths and different physical latencies and so on. So here's experiment one. And just maybe a word about why this matters. It matters because different congestion controllers and different configurations of the same congestion controller might perform amazingly well in some environment and horribly in others. Right? For instance, we know that TCP cubic, which is the de facto for a lot of video traffic, performs very well in some environments, but if there's even a little non-congestion-based loss, it performs horribly. BBR, Google solution, performs well in some environments. If there's latency jitter, it also performs really badly, right? And of course, there's a whole spectrum of behaviors between these two. So in the first experiment, you see the link parameters here. This is actually a very stable network. And we choose a performance metric somewhat arbitrarily. I'll get back to this. But intuitively, what this does is it trade-offs different things we want. We want to send a lot of traffic, but we don't want high packet loss, and we don't want high latency. So this is what these three components of the function show. And we have different configurations. So as I mentioned, this online learning algorithm has configurable parameters. One of them is how fast you start sending. The other is to what extent do you penalize loss. And the third is to what extent do you penalize increases in packet delays. So you see here different combinations. We're actually, to make this simple, keeping the first two fixed and only playing with the extent to which you penalize latency. Notice the differences in performance, even in this simple environment. So the fourth configuration you see on the right. The performance, think of this as the ground truth. We ran a lot of experiments with this configuration, so we know how well it performs. So the number at the bottom, remember it, it's 5.4. Out of these configurations, this is the most you can strive for. Now, what you see here are these different algorithms over time. So they start out basically knowing nothing, right? And then they interact with the link, and they Very quickly, actually, the x-axis is the number of interactions with the link. Think of this as 1-minute interactions sending video traffic across the link. Very quickly, they actually converge to a configuration that's not far from the optimum. And for some of these algorithms, the more robust ones, it is actually the optimum. In the second experiment, we're seeing something very similar, only now there's non-congestion-induced loss. And now we are again looking at 4 configurations. The degree of freedom is in the parameter that represents to what extent we penalize loss. Right? So notice the best configuration is once again there at the bottom, and you see that it attains an average performance score of 2.27 across multiple experiments. Once again, these algorithms are able to, over time, converge to the right congestion control logic. This has huge influence over video quality for the service running on top. So this was a super simple experiment and a super simple example and a super simple algorithm. Right? Why is real life more complicated? Because it was a toy example. Because in real life, obviously, we're not sending over a single link. There's competition with others, and there's temporal aspects to traffic. I'm not expecting it to be the same network conditions right across time. Also, I can't just probe configurations. I want to somehow safely do that. I don't want to probe configurations that are risky, and just probing them might have undesirable effects. Also, we were looking at very simple performance scores. But what I really care about is video quality of experience. Why don't I quantify performance using explicit metrics of video quality of experience? This is actually what we do in the field. I'll talk about this in the next talk. At what granularity should customization be performed? Per individual video session, or do we want to group video sessions, say by service or by IP subnet? And this, of course, affects the location at which this is done. Is this done at the edge, right, at the video cache, or should it be done in the back end based on longer-term statistics? Right, so there's a lot of subtleties here, but the key point I was trying to make is we're somehow very comfortable with the fact that we're injecting video traffic into a network that cares not about whether it's video traffic and what the specific network is, right, in terms of delivering this traffic. Right? I think that can change, and I think that can have huge influence over the way we deliver video and the quality of experience that our users experience. Thank you very much.